You consume it daily. You go through more than you probably realize. You are literally made of it. But how much do you really know about water? Join me, Lake Storywater, and my droid, H2O, as we travel in search of the science behind water and water-related concepts. This is Story of Water. Lake Storywater here, broadcasting from my exploration vehicle, the Aquarius. I'm joined by my droid, H2O. Say hello, H2O.
Hello.
Well, let's dive right into today's topic. Water. H2O. Dihydrogen monoxide. How often do you think about water? How much water do you use? What do you use it for? What do you really know about this ubiquitous substance that allows for life as we know it to exist? What makes water, well, water? Water really is a unique substance due to its physical and chemical properties. Let's explore the nature of water more in depth.
That's a pun.
Picture the Mickey Mouse symbol. A water molecule consists of two hydrogen atoms, which would be Mickey's ears, bonded to one oxygen atom, which would be Mickey's face.
What does bonded mean?
Here's an analogy to answer that. Think of each atom as a ball of Velcro. The hydrogen is the Velcro with the tiny loops, and the oxygen is the Velcro with the tiny hooks. In order for the atoms to stick together, two conditions must be met. One, the atoms must come close enough to each other to stick, and two, the atoms must come together with enough force to stay together. When this happens, the atoms bond to each other, but instead of sticking together with Velcro, it is electrons that hold the atoms together. Electrons are tiny, negatively charged particles that orbit the nucleus or center of an atom. In a water molecule, one oxygen atom shares electrons with two hydrogen atoms. This sharing is called a covalent bond, and it is also what makes water a stable substance. However, the oxygen atom doesn't like to share the electrons evenly with the hydrogen atoms. The electrons are actually more likely to be found around the oxygen atom than the hydrogen atoms. Remember, an electron is negatively charged, so by spending more time around the oxygen atom ends up having a partial negative charge, while the hydrogen atoms have a partial positive charge. Essentially, each water molecule is a tiny magnet. This is referred to as a polar bond, and it gives water some of its unique properties. Here's an experiment you can try at home. Take a blown-up balloon and rub it in your hair. By doing this, you are transferring some of the electrons from your hair to the balloon. Now the balloon is negatively charged in that area. Next, turn on a faucet so you have a running stream of water. Slowly move the balloon closer to the water, but don't let it touch.
The balloon bends the water.
The positive charge of the water's hydrogen atoms is attracted to the negative charge of the balloon. Because each water molecule is like a magnet, it gives water cohesive and adhesive properties. Cohesion is the ability of water molecules to stick to each other. You couldn't have oceans, lakes, ponds, puddles, or even drops of water without cohesion. Adhesion is the ability of water molecules to stick to other types of molecules.
Like how water sticks to the side of a glass.
Yes, that's right. Here's another experiment that you can try at home. Let's use that glass of water to demonstrate another cool property of water, surface tension. Due to the cohesive forces of water, a water molecule is attracted to all other water molecules near it. In a glass of water, all molecules underneath the surface are pulled evenly by all other molecules. However, there are no water molecules above those ones at the surface.
So what happens?
Those surface water molecules still need to bond cohesively, so they actually form stronger bonds with the other surface water molecules that they are near. This makes it harder to actually break through the surface of the water. Think of a tiny water strider bug. As long as its legs are dry, it won't break through the surface. We can do the same thing with a paperclip. As long as the paperclip stays dry and we set it down ever so gently, we can have it float. If you break the surface tension, well, just try again, making sure your paperclip is dry. Have you ever enjoyed a nice cool glass of Kool-Aid on a hot summer day? Or how about a mug of hot cocoa on a cold winter night?
I have not.
Well, I know you haven't, but everyone else can thank the polarity of water for that drink. See, polarity allows for water to be known as the universal solvent, which means that it can dissolve many other different substances. When you put Kool-Aid mix, which is mostly sugar, in water, what happens?
It sinks to the bottom.
Well, yeah, but if you read the directions, you would know that you have to stir the mix. Stirring the mix allows the individual water molecules to get between the sugar molecules that started out as one clump. The sugar molecules, which are also polar, are attracted to the water molecules, and the water molecules can then pull the sugar molecules apart from each other. Water can also dissolve other substances that aren't polar. Think about salt. Salt is what's known as an ionic compound. Unlike covalent bonds that share electrons, ionic bonds gain and lose electrons. Salt consists of sodium and chlorine atoms bonded together. When you add salt to water and mix it like we did with the Kool-Aid, we can dissolve the salt. But what's happening this time is quite different. The water molecules are now actually tearing apart the individual salt molecules. The sodium ions are attracted to the oxygen part of the water, and the chlorine ions are attracted to the hydrogen part. The only type of substance water can't dissolve are those without a charge, which are referred to as nonpolar molecules. An example of this is oil. No matter how much you stir or shake a mixture of vegetable oil and water, the oil won't dissolve. It does make for a cool lava lamp, though.
I guess that's why they say oil and water don't mix.
So here's a question for you to ponder. How did we end up with water on Earth?
I'm not sure.
That's correct. Actually, we're not sure. We know that water existed in the early universe, when the Earth would have still been forming from a swirling cloud of dust, ice, and gas. As more of these particles clumped together, it is reasonable to say that some water molecules also joined in. But there are a few problems with this. One, it was too hot in the early universe for water in the gaseous form to become liquid. And two, there was no atmosphere yet to keep the water molecules bound to Earth. So, what is a better explanation? Possibly, water hitched a ride to Earth on rocky objects like asteroids and comets that collided with an early Earth. There is evidence for this, as the chemical makeup of water found on asteroids is similar to that of water in our oceans. This question, however, is still debated, so although we have some good ideas, we may never know exactly how water came to exist here on Earth. Just be thankful that it did. Now, let's distinguish between two categories of water, freshwater and saltwater. The oceans and some smaller bodies of water, such as the Great Salt Lake and the Dead Sea, consist of saltwater, while most other water you find on Earth is freshwater. Besides the obvious difference of one having salt and one not, there is another interesting difference. Pure freshwater is an insulator, meaning it doesn't allow electricity to pass through. However, it is usually impossible to find pure fresh water with no minerals or any other small impurities in it in nature. Salt water is usually considered a conductor of electricity. Salt water is a much better conductor of electricity, but fish and other marine creatures are usually safe when lightning strikes a body of water.
Why is that?
Simple, really. The electric charge of the lightning, when it hits the water, gets spread out mostly across the surface. The current basically dissipates as it heads downward in the water, and it also loses its charge as it spreads out across the surface. So, as long as an animal isn't at the surface, in the immediate vicinity of the lightning strike, it is usually safe.
Why can't humans drink salt water?
I'm glad you asked. Even though salt water is water, it dehydrates us through a process known as osmosis. Osmosis occurs when a substance moves from an area of high concentration to an area of low concentration until there is an equal distribution between the two. Drinking salt water would mean there's a buildup of salt water outside of your cells. Water from inside your cells would then move outside of your cells to the salt water to try to maintain this balance. When this happens, your cells shrink and your body tries to get rid of the excess salt by having your kidneys produce urine. Urine gets rid of salt, but it also gets rid of water. That water that left your cells now also leaves your body with the salt. Your cells need more water, but if all you have is salt water, this process repeats itself until your organs shut down due to severe dehydration.
Fact: the human body is about 65% water.
Here's another experiment you can try at home. You can actually see osmosis in action. Take a carrot, peel the skin, and cut into several sticks lengthwise. Or you could just take a baby carrot and cut it in half lengthwise. Then fill a small bowl or cup with water and add about 2 spoonfuls of salt. Place your carrot in the salt water and check back in about 30 minutes. You should notice that the carrot is now soft and bendy. That's because the water in the carrot transferred into the salt water, shrinking the carrot's cells. Water is also one of the few elements that can be found in solid, liquid, and gas form at the normal range of temperatures on Earth. Water not only moves physically from place to place, it also moves through the 3 states of matter through the water cycle. To keep it simple, let's just focus on the main mechanisms of the water cycle. First, when there is a body of water heated by the sun, water molecules will gain enough energy to break the bonds between them and become water vapor. This is evaporation, liquid changing to gas. Second, when those water vapor molecules cool down in the atmosphere, they begin to bond again, and you might see the product of this, a cloud. This is condensation, a gas changing to a liquid. Third, when those drops of water that make up a cloud become too heavy to stay suspended, they fall to the ground. This is precipitation, and will fall as rain unless the temperature is cold enough to cause a liquid to change to a solid by freezing and falling as snow, sleet, or hail. Finally, surface runoff occurs when precipitation falls over land and the water moves along the land's surface until it reaches a body of water, allowing the cycle to continue.
Question: how much water is there on Earth?
There are 326 quintillion gallons of water on Earth. That's 326 followed by 18 zeros. Let's break down this insanely huge amount into smaller categories. First, 3.2 quadrillion gallons, or 3,200,000,000,000,000,000 gallons are stored as water vapor in the atmosphere. That may seem like a lot, but it is only 1/1000% of the total amount of water. It is, however, enough water to cover all of the world's land and water to a depth of 1 inch. 97.5% of all the water is salt water, and it's mostly in the oceans, leaving only 2.5%, or about 8 quintillion gallons, of fresh water. Of all the fresh water, about 69% is in ice form stored in glaciers and permanent snow, and 30% is in groundwater that is difficult to access. That leaves less than 1% of all fresh water in lakes and rivers and accessible aquifers, and that is the only water that we can use to drink. But of that 1%, we actually use 70% of it for agriculture and 22% of it for industrial uses. That leaves just 8% of all usable fresh water, or 6.4 quadrillion gallons, for people to use in their homes for things like drinking, bathing, washing, and cooking. To put that in perspective, for every 50,000 gallons of water on Earth, only 1 gallon is available for us to drink. But unfortunately, water is not equally shared across the world. In the United States, we use more water than any other nation. The average American uses 120 gallons of water per day. Compare that to some other countries, such as France, with an average of 77, India, with an average of 38, and Mali, with an average of 3.
How does each American use 120 gallons a day?
Well, here's a breakdown according to the Water Research Foundation. 65 gallons are used for outdoor purposes such as watering the lawn and filling pools. 21 gallons are used for cleaning through faucets, dishwashers, and washing machines. 14 gallons are used for flushing toilets. 13 gallons are used for showers or baths. And 7 gallons are used for drinking, cooking, and other miscellaneous things.
According to my calculations, that means Americans use over 14 trillion gallons of water per year.
Yes, that's a lot. But there's other issues as well. Water pollution is a major problem that can lead to less usable water. There are 2 categories of water pollution: point source and non-point source. Point source pollution comes from identifiable sources, such as waste from factories dumped directly into a river, sewage from a water treatment plant spilling into a lake, or an oil spill from a drilling rig at sea. Non-point source pollution doesn't come from a direct source. Examples of this include pesticides and fertilizers from farms, chemicals, waste products, and even household cleaners and paints that make their way into the water supply from surface runoff of rainwater, as well as trash people intentionally dispose of in bodies of water. Specifically, plastic is becoming a big problem that we're finding in our waterways.
Since there is a finite amount of water on Earth, what can people do to preserve and protect that water?
Another excellent question, H2O. There are many simple things you can do, starting with using less water. Here are some tips for doing that. 1. Fix any leaks you find. 1 drip every second adds up to 5 gallons of water wasted per day. 2. Don't let the water run when brushing your teeth and when doing dishes by hand. This can save up to 4 gallons of water each time. 3. Run your washer and dishwasher only when full. You could save the equivalent of about 33 gallons per day. 4. Install a low-flow shower head and shower rather than bathe. You could save at least 10 gallons doing this each time. Did you know that the average American showers for 7.8 minutes? For bonus savings, try taking shorter showers. And 5. Skip the bottled water, cut down on your meat consumption, and consider buying secondhand clothes instead of new.
Question: how do those last 3 things help to save water?
Well, let me introduce you to the concept of virtual water usage. Virtual water is the water that it takes to produce consumer products. For example, the amount of water needed to produce a 1-liter plastic water bottle, from the raw petroleum-based material to the final plastic bottle, is 2 liters. Plus, it is filled with 1 liter of water, so it actually takes 3 times the amount of water than what you actually get out of the bottle. Regarding meat, animals need to drink water to live and grow too, right? Well, cows consume on average 30 gallons of water per day. This equates to 1,800 gallons of water needed to produce just 1 pound of beef. You don't have to cut meat out from your diet completely. Just switching to chicken instead of beef saves over 1,300 gallons of water. Lastly, every time you buy a new outfit consisting of a cotton shirt and jeans, know that it took 2,767 gallons to produce that clothing. As a bonus, your secondhand clothing purchase also prevents those clothes from ending up in a landfill. A simple internet search will reveal many other steps you can take to help protect what is arguably our most precious resource on Earth. Water. It allows for life as we know it to exist. Without it, we wouldn't be here. So, why not raise a glass of water, preferably from your tap, to toast water? Thanks for joining us on Story of Water. If you liked what you heard, why not subscribe to this podcast on your favorite podcast provider? Let your friends and family know about it as well. Connect with us and listen directly at www.story-of-water.com. Check out the blog or email us feedback. If you really enjoyed the show, become a Patreon supporter. Just click the donate button on our website. Remember, stay hydrated. See you next time on Story of Water.